Is Chiang-Mei Chen. He will talk about the pair productions in the near extremal charged black hole. Okay, go for it.
Okay, it's my pleasure to attend this joint workshop and to have chance to present our research result here. So today I will talk. I'm Chiang-Mei Chen from the National Central University. Okay, so today I'm going to present some of our research work on the pair production. Okay, and this is we consider the pair production in some special background. This is called the near extremal charged black hole. And so I will talk explain why we consider such kind of model. Okay, the outline of my talk is I will first introduce the motivation why we consider pair production and in such particular background. And in our work, in particular, we consider the scalar production and also spinor production. Okay, so scalar particle and also spinor particle. And the charged black hole we consider is the so-called the famous solution in the Einstein theory called the Reisner-Northern black hole. Okay, so what's the pair production? The intuitive picture for the pair production is because the vacuum has a quantum fluctuation. Okay, and the simultaneous pair production just due to some particular mechanism try to transform or this the virtual particle to become a real pair. And the mechanism could be for example, electromagnetic force. Okay, particularly we can the system has an electric field. Okay, and an electromagnetic force can transform this virtual particle to be a real pair, or because the black hole horizon, okay, due to some kind of tunneling effect. So these are two famous phenomena. One is called a Swinger mechanism, the other is corresponding to the Hawking radiation. Okay. So, and we will consider such kind of the such a phenomena in the particular charged black hole background. Okay. So our goal is to consider pair creation in the charged black hole, and technically to investigate such kind of problem is more easier to consider the system as a constant electric field. Okay, and also our main purpose is we want to try to understand what's the holographic description of the pair production. Okay, and the holographic duality is more well studied in the so-called anti-de Sitter background. So we hope we can have some kind of to consider some particular background with the anti-de Sitter structure. Okay. So this is why we consider the charged black hole in the near extremal limit. Okay. So because it's well known the Reisner-Northern charged black hole in the near extremal limit. If we consider near horizon geometry, then there is the ADS2 close to S2. So this is an ADS structure, and the electric field is a constant. Okay. So this is the most suitable background for our purpose. Okay. So because the constant electric field, so we can have hope can solve the system exactly, and because there's the ADS structure is also help us to understand holographic description. Use the ADS-CFT correspondence. Okay. So this is the reference of our work. The first one is cooperation with the Sampyer Kim from Korea, and then this the first paper considered the scalar production. And recently we finished our work on for the spinor particle. Okay, so we will focus on the pair production on the near horizon geometry. So what's the near horizon geometry? So if we draw a picture for the time and the radial coordinate of a black hole, okay, like charged black hole. So usually charged black hole has two horizons, the outer horizon and the inner horizon. Okay. And then we will focus our calculation in this is the blue region. Okay, so near horizon region. And the reason only consider such kind of region because this region contains the horizon. Horizon is inside this region, and the horizon is the mechanism for the Hawking radiation, and also the electric field in this region, there's the dominant electric field. So even the Swinger mechanism also the major contribution is appear in this region. Okay. So this is the reason we only focus on this near-Holland geometry region. And the other reason is because this region has ADS structure, and so we can consider the holographic description for such kind of the pair production process. Okay, but when we consider the near extremal means the R plus and R minus are very close. Okay, in such special cases. Okay, so and then how we compute the pair production information. So for example, we consider a pop field. So either the charge mass scalar field or Spinor field, and then we try to solve the Klein-Gordon equation or Dirac equation in such background, and then in this case we can find the exact solution. And from the exact solution, we can consider the asymptotic behavior at the outer boundary and the inner boundary. Okay, and we impose the particular boundary condition. So there's no particle flux come in from the outer boundary. Okay, and so there are remain three flux can have a very intuitive physical picture or physical interpretation. Okay, so this outgoing flux on the outer boundary. This look like the transmit flux. This is like a pair produced particle. Okay. And at the inner boundary, these two flux can be identified as the incident flux and the reflect flux, and this part is corresponding to like the pair, virtual pair particles, and the reflect part is like a reannulate. So most of the virtual particles reannulate, and only part of them can transmit to becomes the real particle. Okay. So this three flux has quite intuitive fixed picture, and then from this picture we can try to compute the pair production. The physical quantity related to the pair production. So there are the two quantities, alpha square and beta square. This is just the Bogoliubov coefficient. Okay. And one is related to the vacuum resistant amplitude. Okay. And so this we can compute this from the incident flux divided by the reflect flux. Okay. And this is just tell us how vacuum resists to produce the real particle. Okay. So for example, if alpha equal to 1, this means all the virtual particles just completely reannulate. No any real pair can be produced. And the other beta square, just like obviously this is just the carry the information about the transmit part. Okay. But our more interesting quantity for us for the holographic comparison is the absorption cross section. Okay, this is simply just the probability of the pair production, just the pair produce the flux divided by the virtual flux. Okay. And this is the most important because we want to compare with this quantity with the two-point function, okay, or absorption cross section in the conformal field theory side. And the flux conservation just relate to the Bogoliubov relation. So this is the picture and the motivation and also the strategy how we compute the related the quantity. Okay, so the next is just the detailed calculation. So we consider first let's focus on the scalar production. So if we try to get the near Holland geometry of near extremal ion black hole, this is the result. Okay. So the matrix of the near Holland region contains this blue part is just like a ADS2, and the green part is just the S2. Okay. So that's the ADS2 cross S2 structure. Okay. And in this region, the electric field is a constant, 1/Q. Yeah. So this is the more technical detail explain there's the ADS cross-S structure and the electric field is a constant. Okay. And we want to try to solve the dynamics of the massive charge scalar field in this background. Okay. So this is the Lagrangian of the mass scale charge scalar field, and the capital D is just covalent derivative plus the coupling with minimum coupling with the Ewald gauge field. Okay, so this standout we have the Klein-Gordon equation, and for the flux we want to consider the radial direction of flux. So this is the formula to compute the flux. Okay. And we assume, because of the spherical symmetry, we assume the scalar field have such kind of the form, and substitute this into the Klein-Gordon equation. And this Klein-Gordon equation can be separated as a radial part and the angular part. Okay. And the angular part is just the standard spherical harmonic equation. Okay. And this is important because it tells us what's the value of this separation constant. It's just the L times L plus 1, and L is the integer. And the more important, we needed to solve this radial equation. And the radial equation is easy because even if we don't know how to solve, we just type this equation into the Maple Mathematica. Okay. And the software will tell us what the solution is just hypergeometry function. Okay, so we have exact solution, then we can do the analysis of the asymptotic behavior and try to identify the ingoing mode, outgoing mode on the boundary and on the inner boundary and outer boundary, and try to impose the suitable boundary condition and calculate the production rate. Okay, but when we try to solve find a solution, we found there's another additional condition. Okay, to ensure the existence of the pair production, because the solution corresponding to pair production the solution can generate from the horizon can propagate to the infinity. Okay, and the propagating mode requires this inequality. Otherwise, this is just the decay mode. Okay, cannot propagate. Okay, so we have this kind of the inequality, and this inequality in detail is actually exactly corresponding to the so-called BF bound of just the instability of the in the ADS space. Okay, so it's the nature of this kind of pair production correspond to the unstable mode. But this inequality has an interesting implication, because from this inequality, a necessary condition is the Q square must greater than M square. Okay, remember the Q square and Q and M are the charge and mass of the scalar field. So if we use the naive charge and energy conservation, this means the black hole during the pair production will lose charge more than lose the mass. Okay. So this means the pair production will preserve the cosmic censorship. Okay. So this avoid the negative singularity. Okay. Okay. So now execute the detailed calculation. This is the result. Okay. So we can exactly find the closed form of the alpha square and beta square. Okay. And then in this expression, there are three parameters, A, B, and A tilde. This is just combination of the parameter from the scalar field and the black hole. So small q is the charge of the scalar field, and capital Q is the charge of the black hole. Okay. And here L is an integer. And more important is this absorption cross section. Okay. The expression of the absorption cross section we can have is cross expression. Okay. And moreover, we also compare. We take some particular limit, and we compare with the earlier study on the pair production. This we can actually reproduce the Schwinger formula. So this confirms our approach is really capture the result of pair production. So for the holographic description, we want to compare with this absorption coefficient with the 2-point function in the CFT, because the expectation is the iron black hole have the CFT2 dual. So there are some earlier results, including the work of our group and also other group. So the Kerr and the iron black hole have the CFT duality, CFT2 dual discretion. And because of the CFT2, they have the universal or standard formula of the absorption cross-section. Okay. So once we know the temperature of light and the moving mode and also the conformal weight of the dual operator, and then we can write down the absorption cross-section from CFT. Okay. And the relation of the temperature is already known, and the central charge. So the central charge are already known in the previous research. Here I did not have time to explain this, but just by considering the symmetry of the geometry and try to formally quantize the algebra, we can obtain the central charge, and also from comparison with the cosmic operator, we can have some temperature. Okay, so just okay. This result I just copied from the previous research work. Okay, so now in order to compare the absorption cross-section, the misinformation about is the conformal weight, because this conformal weight should corresponding to this the dual field. So for example, here we consider the scalar field, we should have the dual operator corresponding to this scalar field. And this conformal weight actually can be read out from the asymptotical form of the solution. Okay. And it's turned out the conformal weight is one half plus ID. Okay. B is just the parameter here. Okay. And the important issue is here. There's an imaginary pi in the conformal weight. So the conformal weight of dual operator is complex, and this is corresponding to the unstable dual operator. Okay. And once we can read out the conformal weight, and then we use the standard approach to identify the corresponding energy and chemical potential. Then we can compare this equation with what we compute from the gravity side, and these two expressions match very well, just up to some numerical factor. Okay. So this is the confirmation or support for the holographic dual discretion of the Spinor production process, and we can generalize this scalar analysis to the Spinor field. So Spinor field, first we just consider, okay, write down the more general spherical symmetric matrix and the U1 gauge field. So explicitly we will find a Spinor solution for this particular background. Okay, for the near-extremal of near-extremal Rn, the function f should be this form, and the rho is just simply just the constant q. Okay. But for formulating the Dirac equation, we just use the general, because it's just the more abstract notation. Okay. So for this spherical symmetric space-time, and this is the Dirac equation. Okay. And the technical issue is the Dirac equation contains the connection, the contribution from the connection. But for the spherical symmetric, this part can be absorbed by a rescaling. Okay. So this kind of property can largely simplify the difficulty of the calculation. Okay, we do this kind of the rescaling of the Spinor field, and then we can absorb the connection term into the derivative, okay, of this scale factor. So the equation can be the Dirac equation can be simplified. Okay, and then we just try to expand the Spinor field, okay, in terms of the so-called spherical spinor. Okay. And the spherical spinor is just like very similar to the scalar case, because scalar case, the angular part, the solution is a spherical harmonic. And for the spinor field, the angular part is also also like okay, just like a particular kind of the spinor, and this spinor component is just given by the spherical harmonic, some particular particular combination of the spherical harmonic. Okay. Here I did not write down the detail about spherical spinor, okay. But this can be found in some books, or even in our paper, the appendix we give the detail of the property. But more important is these two spherical spinor has very good property with respect to the gamma 0 operator, gamma 1 operator, and this so-called kappa. Kappa is just a particular gamma 2 and combination of gamma 2 and gamma 3. And all these three operators just appear in the Dirac equation. So gamma 0 here, gamma 1, and gamma 2, gamma 3 combination. Okay, factor out the 1 over log. Okay. And this spherical spinor has a very just like a similar to just like an eigen spinor of these three operators, but not exactly because for example the gamma 1 will switch the phi plus to the phi minus, okay, and the kappa also. But similar, just like they have some kind of the eigen spinor. Okay. And this property allows us to separate the Dirac equation. And here important is the parameter, the quantum number is the angular momentum, and the J, and J is related, the kappa is related to the J. Okay, and this is the quantum angular momentum of the spherical spinor. Okay, so then we can separate the Dirac equation, and what we need to solve is just the radial part, the radial equation. And this radial equation is more difficult, so it took us more time because we cannot substitute this to the mathematical method and to get the solution. We needed to try to find suitable way to solve this equation. And after a while of work, we found a particular way to solve this. Firstly, we need such kind of combination and of these two functions. Okay, and then in terms of this more convenient in terms of the z coordinate, and then we do some kind of the rescaling. After such kind of process, and we found the three particular combination also appear. I use also A tilde and B, and this is very similar to the almost identical with the scalar field case. Okay, A and A tilde are same as and the difference is only B. So the B parameter for the scalar field here is the integer, but for spinor field this is half integer. Okay, this is only the difference. Okay, so then this is the equation actually can be transformed to the hypergeometry equation, and the solution is hypergeometry function, again the hypergeometry function, and then we can do the similar analysis, okay, for the spinor field case. And for the spinor field case, we also have this inequality, okay, in order to have the to ensure the existence of the propagating mode. And this inequality also get the similar result. Okay. Just preserve the cosmic censorship conjecture. And then we can compute the flux. Okay, the flux for spinor field is a little bit more complicated. We can have the flux density and the radial directional flux, and then this is the result. Okay, so the difference with the scalar field case is I mark in the red. So if we change the hyperbolic sign to become hyperbolic cosine, and hyperbolic cosine to hyperbolic sine, and this is the same. This will transform back to the scalar field case. Okay, so this the color part is just a difference, and also of course the B. Okay, B also has a slight difference. Okay, we also can compare this. We can read out what's the conformal weight, and this turned out for the spinor field, the conformal weight of right-handed and left-handed has slightly different, but they both have a imaginary part IB, okay, similar to the scalar field case, and this is corresponding to the unstable operator. And if we use this and try to substitute to the compare this expression with the standard 2-point function in the conformal field theory for the fermion, and this also match well. Okay. Okay, so this is the basically our main result. And so our result, if we consider the phase diagram, so we only consider near extremal case. So suppose this is the phase diagram for the black hole. This is the mass and this is the charge of the black hole. And the extremal, this means the mass equal to charge. So we consider only the black hole in this region. Okay, near this line. And we found the pair production, the black hole will evolve to this direction, but not in this, not toward to the naked singularity. So pair production really ensure the cosmic censorship conjecture. Okay. But of course, our analysis only can apply not far away from this extremal line. Okay. So it's quite interesting to see how the non-extremal black hole, what's the final state of non-extremal black hole during the pair production. But it's more difficult, okay, because I don't expect we can have any analytical result for non-extremal case. but at least near the extremal we have quite interesting result. Okay, so let's summarize. So we consider the simultaneous pair production in the near extremal ion black hole, both the scalar field and the spinor field case. And we can exactly get the probability of coefficient and also the absorption cross section. Okay. Then those results can be expressed can be found in the closed form. Okay. And then the pair production is holographic is due to an operator with the complex conformal weight. And then this also actually the absorption coefficient on both sides are matched pretty well. And also the interesting consequence is the cosmic censorship is preserved during the pair production process. Okay. So this is the main result I want to report. Thank you.
Thank you very much. Any questions, comments? Let me ask one question. Quick question. So when you talk about Spinor production, when you talk about the conformal array, there's HL and HR is different. Is there a way that simple way to understand HL and HR?
Yeah, but in the conformal field, for the spinor field, the difference between these two conformal should be 1/2. Yeah. So this is because the spinor part, even in the conformal field, this also will know this should be the difference should be 1/2. Yeah. Because the 1/2 spinor field.
Okay. Yeah. Any other questions? If not, let's thank the speaker again.